coming to our final Boeing talk of this academic year. It's my pleasure to introduce Professor Beatrice Pelloni. Beatrice is a specialist in lots of things related to PDEs, especially kind of those things that you would not get anywhere near in a very traditional first course on PDEs. Beatrice got her PhD from Yale. After that, she became a postdoc at Imperial College before going on to tenure track and tenure positions at Reading University and since 2016 at Heriot-Watt. Beatrice has received numerous awards. She was the Olga Todd Prize Lecturer at the 2011 XCM conference, and more recently the Mary Cartwright Lecturer of the London Mathematical Society in 2019. She's a fellow of the IMA and of the Royal Society of Edinburgh. Please join me in welcoming Beatrice.
Thank you. Well, first of all, can I thank the Department of Applied Maths and Bernard for the invitation and the really gracious hosting of my visit here. I've really enjoyed myself so far immensely. I will not enjoy myself quite as much in the next hour. Okay, so this is my title, and it's a bit cryptic. Discontinuous linearized waves, the Talbot effect. Revisited, not many people know what this Talbot effect is, and discontinuous and linearized waves doesn't seem to make a lot of sense. So I'll try to, first of all, explain what it is that I will speak about. Okay, let's see if I can actually... Right, so let me tell you what I will talk. The first thing is I will just tell you about the Talbot effect and use two very well-known linear PDEs. Everything, more or less, everything will be about linear, not all. Linear Schrödinger and Airy equation, which is just the linear part of KdV. Okay, so linearized. And then I want to talk about more general linearly dispersive waves. So I will take other important water waves that I actually first encountered when I was a PhD student, Benjamin Ono, and the intermediate long wave equation. They are models, reductions of the full water wave model for different depth domains, so BO for infinite depth, the intermediate long wave for intermediate depth. They're non-local PDEs, so quite different from KdV, say, for which the linear part is the Airy equation. Then I will try to see if we can relax this notion of Talbot effect. I'm calling it dispersive quantization at this point. I'll go over all these terms. And finally, I will give you a few pictures of what happens if I add nonlinearity to all this. So hopefully this gives you a bit of a roadmap. If you get lost, just scream. Okay, so this is Mr. Talbot. He was one of these British polymaths that had his hand into a lot of little different things. He was very curious, wrote very abundantly. One of the things he really was into was photography. And in fact, he was, of course, a wealthy landowner sitting in a large estate somewhere in the English countryside, so he had ease to do these things. And photography was just coming up. In fact, the very first, oldest negative, photographic negative, still in existence is one of his. It's not this one, but it's one like this one. He didn't only photograph these kind of things. He photographed a lot of flowers, plants, and studied various things. But one of the things he was very intrigued by were latticed windows, which are pervasive in old large buildings and cathedrals and abbeys in England. That's one that you cannot see terribly well, but this is one that you can see a little bit better, and is typical of the kind of things that he was doing, that he was trying to photograph. I don't know why, really, but anyway. And this is where he observed this phenomenon. When he was taking photos of things like this, where there is a pattern on the glass that interrupts the flow of light, he noticed that the pattern of the grating, especially, these are approximately periodic patterns, was reproduced at certain fixed distances. And he was very intrigued by this. He wrote a lot about it, and that's what he wrote. So he reports observing that a regular alternation of numerous lines or bands having their direction parallel to the lines of the grating, so somewhat reproducing the grating, you could observe those, and it was curious that although the grating was greatly out of the focus of the lens, the appearance of the band was perfectly distinct and well defined. And really, he observed it at length and wrote about it at length. And this revival of this grating pattern was then christened about 100 years later the Talbot effect. So this is what Talbot effect refers to. Lord Rayleigh was able to compute the distance at which this phenomenon appears, and then everybody forgot about it, and nobody studied it until about the 1980s, maybe 90s even. Okay, so it's quite curious because, in fact, mathematically it's not very difficult to explain, and it is observed in a lot of things. So this is a modern rendition of it. So you have to imagine light coming in here through these holes here. The rest is blocking the light. So let's say you put a 1 where the light goes through and a 0 where it doesn't. And at certain fixed distances, and the distance is a over lambda square, you have an exact reproduction of this pattern. And in between, there is a sort of scaled or version of it, but certainly with the same pattern. And yeah, it's a self-imaging phenomenon. It's really not only an issue of light. It's very generic of any coherent wave interfering, and it has then, since the 1980s, 90s, it has been reproduced and demonstrated and observed in a lot of other experiments. As you can see here, actually, there is a paper that came out just months ago where it's a sort of classroom experiments where this phenomenon has been reproduced with surface gravity waves in a tank, which is kind of cool. And also in quantum physics. If you look quantum revival on Google, you'll see loads of pictures of the probability density of a particle, of a quantum wave function in a box, things that look, and they're called quantum carpets because they look like this, and they look like a bit like carpets, okay? So it's just some nice coherence reconstructing an initial condition that you can see with the naked eye. You can sort of follow with the naked eye what the pattern is. Okay, so let me just give you a little bit of a very simple explanation. So that's what the first mathematical paper on this was by Michael Berry and his collaborators. They also did some optical experiments, but then they modeled this phenomenon using the linear Schrödinger equation, this equation, taking, say, a step initial function. So you look at it on a periodic, on a torus, let's say 0 to pi, and you say that the initial condition is 0 on half of your interval and 1 in the other half. So that's just the setup. And then you go and look at what the solution looks like, and you find that if you pick a time, so first of all, let me say this initial condition is not continuous. So you don't really expect the solution to be twice differentiable. So when I say solution, I really mean in a weak sense solution. However, the funny thing or the interesting thing is that it has a meaning pointwise. You can give it a meaning pointwise everywhere. And at times there are rational multiples of the period, in this case, rational multiples of 2 pi. And I will call these times rational times, but really it depends on the period. It's just rational multiples of the period. The solution reproduces a translated scale version of the initial discontinuities. Okay, that's more or less what we have seen in those pictures. And these are the papers that, well, Berry's papers were the first one, and he looked at linear Schrödinger. Then there were some other papers of Peter Olver, and he did the same thing with Airy, so linear KdV, and that's when I got interested in it, and I'll tell you the story when I get to it. And he called this effect, because he didn't know about the Talbot effect. He noticed, he observed it in numerical experiments, and he called it dispersive quantization. And then there is a nice PDE books by Erdogan and Tsirakis, who have a general theorem for every polynomial dispersion relation. And I'll show that as well. What you cannot really see in those experiments is what happens at different times. Okay, so these are very special values of the time that you're picking. But if you pick a time generically, what happens? Well, what happens, and this is a lot more difficult to prove analytically, is that if you start with an initial condition that has a discontinuity or two, like ours has two discontinuity, one in the middle and one at the endpoints, at generic time, the profile, the solution, is continuous. So it regularizes that discontinuity, but it becomes nowhere differentiable, very oscillatory, and in fact, it has high fractal dimension. So there is a real dichotomy in behavior at different times. And this was done by strong guys in real, pure mathematics. Rodniansky, Kapitansky, Skolkov was actually the first one to study this and describe the fractal dimension of the solution at generic times. I won't speak about this. I'm just telling you that there is this dichotomy. I will just maybe show you pictures, but I won't tell you very much about the techniques that go into this. You need really sort of hardcore estimates, Bourgain estimates, and stuff like that. And there is a paper from just the turn of the century whose title is, does a periodic quantum particle know the time? Because really what is most intriguing is this oscillation between times, rational times where the initial discontinuities reappear, and other times where they are breached and the solution is continuous. And rational times are dense in the irrational. It's all very mysterious. Let me show you some pictures, just so that pictures tell the story a lot more clearly. So this is just my step initial condition, 0 and 1. I'm looking at linear Schrödinger equation, periodic boundary conditions. And if you just take the Fourier series solution of this, which you can write down explicitly because the Fourier coefficients of this particular functions are very easy to find. The Fourier series, of course, only converges in L2. Actually, this is a bounded variation function, so it converges at every point of continuity pointwise, and at the point where the function is discontinuous, it converges at the average, so in this case to 1/2. So you can give it a meaning even pointwise. And so I take the Fourier series solution, I truncate it at, I don't know, here probably 200 terms or something like this, and that's the kind of solution pattern you see. Blue is real part and red is imaginary part. And if instead you pick different type of times, there is a vastly different behavior. So this is the Talbot effect, and this is the fractalization effect that I was talking about. You can do that with other initial conditions. The step is not at all special. It just is a sort of simple example of an initial condition with discontinuities. But here, this is another student, former student did this, but anybody can do them. It's really easy. So that the function is only 1 here and 0 everywhere. This sort of approximates a delta function. And the moment you step time, this is a very short time, all hell breaks loose. You can see this is a very widely behaving solution, but if you pick your time as a rational time, then it quantizes and it reproduces this initial pattern. several copies of it, rescaled and translated. So let me, a slightly more precise and more encompassing mathematical description of what this effect is. Suppose, let me do it on linear Schrödinger, which is, after all, has been the prototypical model for this. Again, just periodic. I'm not just with an initial condition in L2. It could be anything. It could be smooth. It could be not smooth. So what we call revival is the property that I will prove for you that at any rational time, so any rational multiple of the period, the solution is obtained as a finite superposition of translated copies of the initial condition. That is irrespective of the class of the initial condition. This always happens. And that's quite striking, because it means that if you give me one of this time, you only need the value of u0 at a finite number of points to give me the function, the solution. If, in particular, your initial condition happens to have discontinuity, it's maybe piecewise smooth with finite or countable jump discontinuity, so that describes a bounded variation function, then, again, I stress the solution is only in the weak L2 sense, but you can be interpreted pointwise, and it has finitely many jump discontinuities. If you have finitely many jump discontinuity in the initial condition, that's what I will call dispersive quantization. That's what was known as Talbot effect. And at any other time, but if u0 is in BV only, if you start with an initial condition with a jump, the solution is continuous, but nowhere differentiable, and you can actually compute, not just in one dimension, also in several dimensions, in boxes, say in Rn, the fractal dimension of the graph. Okay, so that was linear Schrödinger, and this is Airy. And this is when I got interested in this problem, because I went to a talk given by Peter Older, and he was talking about this. And then I, in my life before, studied third-order boundary value problems for third-order problems like this, and for KDV quite a lot. So I immediately thought, that's periodic boundary conditions. What about other boundary conditions? And I wanted to see. But anyway, he said he was looking for exercises for his PDE book, and he wrote the exercise to write the Fourier series for the solution of this Airy equation when you start with a step function, which is here. This is computed summing the series, as you can see, because there are Gibbs phenomena all over the place at the discontinuities. And he did that. First, he solved it to make sure that it was a solvable thing, and he plotted it just to make sure, and he plotted it at the times that anybody would pick to see what happens, what shape the solution has. This was already quite, well, maybe unexpectedly rough, given the initial condition. But then, and I don't know why, because as I said, he had no knowledge of the previous work of Berry, he decided to plot it at these other times. And again, this quantization popped up. And he was intrigued, he studied this, he wrote an article for maybe a Mathematical Monthly or something like this, just describing this phenomenon just for this particular boundary condition. And so that's an example of what I called revival. So here, if you start with a not differentiable but continuous initial condition, you can see that if you pick times that are multiples of pi, this corner reappears in different places. If you pick another time, it doesn't. But you don't have fractalization. Fractalization is really generated by those discontinuities, as I will try to wave my hands to explain. So that's the revival effect. Here I've chosen a feature that I could pick again in the solution. If you have a generic functions, maybe you don't pick the feature out so easily. But that shows very clearly that that's always valid. Whereas, as I said, if you start with something that has discontinuity at the beginning, and here I've zoomed in the solution at 3 pi over 4, for example, and you see at this exact time, it will have discontinuities. Because this is a truncated Fourier series solution, it shows you Gibbs phenomena at the 2 points where there is a discontinuity. If I move just a little bit away from that and I pick 3/4 of 3.14 instead of pi, all these oscillations appear. And I will get back to that after I say why revival works. So this is the general theorem that then was only in 2016, although it's not very difficult to prove. If you have any dispersive equation of linear dispersive equation of this form, and this is just a polynomial, and if I write it like this, I guarantee that the equation is dispersive. I take an initial condition and periodic boundary conditions, and then I denote by U0 star the 2 pi periodic extension of the initial condition, because I will need to evaluate it at points that are outside my interval. You can write a nice formula at time that are rational multiples of the period. You can write, you see, that's really nice. The solution is given by a finite sum with some coefficients that are just functions of this index and of P and Q, which are the two coprimes that give you the rational multiple you put here, and then the initial condition evaluated at some translated points. And the translation depends on Q. So everything is, and the number of terms in this sum depends on Q, the denominator of this multiple. Okay, and these coefficients are just Gauss-type sums. These are very common sums in number theory, and really the proof is arithmetic. It has to do with the modularity properties of the exponent of the exponents in the exponentials, and it's really quite elementary. I won't give you the whole proof, but just to say what it is based on is just the fact that if K and H are congruent mod Q, then also P and PK is congruent to PH mod Q. So you have the same modularity in the x exponential e to the I kx as you have in the t exponential with the e to the I p of k t. And then the fact that if you translate in x, that corresponds to just multiplication in Fourier space, and that the sum of all nth root of unity vanishes. If you do this, you really see that there are a lot of aliasing in the Fourier series representation, and you can combine all these congruent terms and get a finite sum out. It's only valid at rational time. The proof of fractalization is a lot harder core. Okay, it requires a lot of analysis. So it only happens when you have a rough initial condition. Whereas this formula for the solution based on finitely many copies of U0 is valid for any U0. If I use that finite sum formula to plot the solution instead of the truncation of the Fourier series, suddenly you really see this is a solution with where the multiple is 10 over 514. So I do expect many, many copies of the initial condition. This is starting from just a step. It's taking that step, scaling it, translating it 514 times, possibly. Okay, and that's what you get. But you can see it very well. And here you don't have any Gibbs phenomenon. You don't have all those spurious vertical lines. For comparison, if you did that with the Fourier truncation, well, if you zoom in, you'll still see the pattern, but it starts looking pretty wild. So you can believe that when you increase the denominator in your rational multiple, you produce many oscillations from Gibbs phenomenon, and you're unable to kill them when you go to infinity, even to. And that's basically what happened. Okay, so really this fractalization phenomenon comes from the solution trying to close the gap in all these jumps, and when these jumps are all over the place, it becomes oscillatory and fractal, of fractal dimension. Okay, I have said that These were all dispersive, but in fact, I didn't tell you what dispersive was. You probably know, but let me just make sure that we're all on the same page. So linear Schrödinger and Airy equations are example of such equations where basically you call an equation dispersive if this is formally a solution and omega then is the dispersion relation. And in my theorem, I always had a polynomial as a dispersion relation. Okay, for linear Schrödinger, it was k squared, and for Airy, it can be plus or minus k cubed. But in any case, polynomial. And that's the only case that the theorem covers is polynomial with constant integer coefficients. In fact, rational coefficients is easy to do. What about non-polynomial? Yes? No, rational, not real. I didn't say real.
No, but I mean real valued.
Yeah, yes, real valued. Yes, otherwise it's not dispersive.
Oh, that's what I meant.
Yeah. Okay, so what about dispersion relations that are not polynomials, which for water waves models are all over the place, right? The full dispersion is this, and then the very many reductions that you can do depending on your interest, take various different forms. Here I've listed some, by no means all the possible ones. So Peter Olver, after he found this linear dispersive quantization phenomenon for Airy, with a student, Gong Cheng, did quite an exhaustive numerical exploration of what happens if you start with a discontinuous initial condition and you have an evolution with this kind of dispersions. And what he found heuristically, and this was only purely based on the numerics, is that if you impose boundary conditions, look at the linear dispersion that these dispersion relations drive, you observe quantization and fractalization only if the dispersion relation is asymptotic to k to the alpha with alpha greater than or equal to 2. And in fact, he also makes throwaway remarks that alpha probably needs to be an integer, and I agree. I think it has to be an integer. So after I had first got interested in this, we agreed to get together, do a research in groups project to study these non-polynomial dispersions, which, for example, in the BO case, that's one we studied, corresponds to a non-local PDE. Okay, so the non-locality is not in the nonlinear term. So the linearized PDE also is non-local, is given here. H is the Hilbert transform, but in the periodic setting, the Hilbert transform kernel is just a cotangent kernel. And in Fourier space, so the dispersion relation is just k mod k. It was on the previous slide as well. So it's not a polynomial because it has that, but it's not that far away. So we sat down and, well, these were the pictures that you can produce if you start with a step function, because you have the dispersion relation. You can write the Fourier series, and that's, again, it's just truncating the Fourier series. At generic time, you starting from the simple step function, that's what you find. Whereas if you pick these rational times, there is something quite different. It's not exactly the same quantization as before. These are not step functions, but they certainly have a structure. And, well, here is mainly this cusps that you should, Mathematica doesn't plot them, but they are infinite cusps. But if you pick other times, you also see discontinuities, like here, here, in many other places. Okay, so there is clearly a dichotomy in this case as well. It's not quite the same phenomenon as the Talbot, but so we set off to try and see if we could do anything to explain this mathematically. So the powerful representation as far as understanding why this phenomenon appears, or if it appears, is the finite sum representation. So we started trying to do that. Can we write the Fourier series for the solution of this problem, which is given here explicitly? This is the explicit solution starting from a step function. So maybe collect terms, try to do something, and we found that we could write it as a finite sum in terms of these functions here, which, as you know, maybe you don't know, but Peter Olver is the son of Frank Olver, and Frank Olver was the absolute top specialist in special functions. He's responsible for the digital library of special functions. He's done a lot of work, very detailed. He was the top experts, and Peter, as his son, has some affinity with them. So he immediately thought that this could be something of a special function. And in fact, it's him who found that these are special functions listed in the digital library and probably in Abramowitz and Stegon as well. And they're called trigonometric hypergeometric functions. I had never encountered them before. There is a lot of structure to these special functions. There are two types. Okay, there are the ones that have sines and the ones that have cosines, and they're called trigonometric because they are obtained by evaluating the usual hypergeometric functions on the unit circle. And there are lots of identities about these special functions. For example, the derivatives are arranged in these chains. This is just structural stuff. You can write them in an alternative way as a sum of some log terms and some cosine terms, and you can study anyway. This is all done for you in this library, and you find that S, the ones that we're interested in, has jumps of a certain height superimposed with a logarithmic cusp, so these infinite cusps, and pointing up or down. So the jumps and the cusps are not mysterious anymore. They come from the structure of these special functions. That still didn't tell us anything about where the initial condition is. How does the discontinuity of the initial condition come in here? Of course, this is here because I chose that particular initial condition. So this is only valid for that initial condition. Okay, so this is just to plot some of these. And in these, Peter manually extended the cusps, not really to infinity. He couldn't do that, but longer than they were. And as you see, they're both cusps and discontinuities in these special functions. And you can write an expression for their distributional derivative, which has both delta functions and cotangent function. Now that's quite spooky because the periodic Hilbert transform kernel is a cotangent. And delta functions are what usually give evaluation of something, right? If you take convolution. So once we had this, well, a posteriori it's obvious, but it took us a while to understand how to use it. So what we really wanted was a finite sum that explicitly involved the initial condition, in our case, these step functions. So one strategy that you can think of is to try and describe what the fundamental solution looks like for this, okay? And then once you have the fundamental solution, you can just take the convolution with your initial condition and hope for the best. That's actually how Peter had given his proof for the linear KdV. So the issue was find a representation for the fundamental solution for this problem in terms of these special functions. And so what happens, it feels like a bit miraculous, but is that if you take as your initial, so we had the step function. This is just the step function written out. Instead of that, we took a different initial condition, the first one of these functions that happens to be exactly this expression. So if you take the derivative of this, you have a delta function from this sine term. Okay, so that's progress. When you're looking for a fundamental solution, you want delta functions to appear. And actually, for this particular, this is still simple. You can compute the Fourier coefficients exactly. You can see how they sum up with all those sines terms. And you can write the expression for the solution in terms of these special functions, again, explicitly. And then if you want to involve, to represent a delta function, which is what we're trying to do, so that then we can take the convolution with any, that's what, so the fundamental solution is the solution starting from a delta function. So we want the delta function as our initial condition. And the delta function is just the derivative of this function plus 1 over 2 pi. We know that the solution for this function, so we just differentiate it, and we get the solution that starts from a delta function, adding 1/2. So here is a representation of the fundamental solution for this problem. So now this is independent of the initial condition I use. But if you take the convolution and remember what these derivatives look like, they look like delta functions and cotangent terms. And so if you take the convolution of that with u0, that will give you your solution at any time, but at time that is a rational, that formula is only valid at rational times. So at rational times, the solution is a finite linear combination, not just of translates of the initial condition, but also translate of its periodic Hilbert transform. So that was really neat, and we were really happy with it. And so we went and also looked at other non-local problems just to see what we could say. So, and this, I will only go a couple of slides on this, but this is the other model, the intermediate long wave equations. I should say the full nonlinear equations, both BO and ILW, are integrable. However, integrability has nothing to do with it. We're talking about a linear effect. So this is what, it's again non-local with this cotangent, hyperbolic cotangent kernel, and the dispersion looks like this. Okay, and this model interpolates between the infinite depth BO and the shallow depth KdV. Okay, and in fact you can write, and this was all the work really, writing the solution in terms of the for the intermediate long wave equation in terms of the solution for BO at a translated in this way plus something, and proving that the something was a continuous, in fact, C infinity function. That means that if I start with a discontinuity, that produces either a discontinuity or a cusp in the solution of BO. The continuous function will certainly not kill the discontinuity or the cusp, the infinite cusp, so they will stay in my solution. So in some weaker sense, this again has this dichotomy between irrational and rational times, and this is a picture. This is with delta equal 1, so it's really a middle of the way case, but it's really almost identical to the BO solution. The other term V is exponentially small, so you don't see it, and it's just translated. And you can also see that in the delta goes to 0 limit, you get exactly the behavior of the linear KdV. I just want to mention that there are also cases when things fall apart. And for example, a very simple case, the first one I looked at, so the next thing that one could do, I won't talk about it at length, is changing the boundary conditions and seeing how robust this is to going away from periodic boundary condition. And the first thing you can do is looking at quasi-periodic boundary condition. This is as close as you get to periodic conditions. And if you look at these conditions for linear Schrödinger, that's just really a translation of a periodic problem in Fourier space. So nothing changes, and you have the revival and quantization effect just as for the periodic case. However, if you look at Airy, that wasn't what we found in the pictures. And so we couldn't understand, but once you well, there is a very neat and very simple trick that tells you why this happens. So if you start with u0 is your given initial condition, and you take the solution starting from this modified initial condition, translated, and these are just those Gauss sum coefficients in the Erdogan and Sirakis formula. So this is really the solution of the periodic area with this initial condition. And I take that as my new initial condition and take the solution of Schrödinger with V0 as my initial condition. So this now seems very involved. If you write it all out, it's very clear why you can do that and why it's useful to do that. And what happens is that the solution of your original area problem then you can write in terms of translation and some exponential that don't matter really as the solution of Schrödinger at a different time. So the solution of area at a rational time is the solution of Schrödinger at a time that is only rational if theta is rational. And if theta is not rational, you kill it. You kill the revivals. And that's exactly what we saw in the numerics. Okay? So the third order problem is a lot more delicate. It's not just periodicity in time that gives you the revivals. There is so much more delicate modularity in the exponentials that plays a role. And so we thought, okay, can we relax this notion? And so this is what I did before. I would say that the revival property holds the strong periodic, if you want, revival property. If you can write the solution at rational times as a finite superposition of copies of the initial condition. And I will say that a problem as the weak revival property, if you can do the solution, you can write as that plus a continuous function. So if you start with discontinuity, this continuous function will alter what happens, but the discontinuity will still be there. Okay, and we have done a lot of examples of which boundary conditions allow you to prove a weak revival property and which don't for the linear problem. But the more interesting thing is about the nonlinear problem now. Let me give one linear example. This is linear Schrödinger, Robin boundary condition. These are the simplest Robin boundary condition. They interpolate between Dirichlet and Neumann problems, which are both essentially periodic. Okay, so if you do that, you can see that you have a dichotomy, but it's not a revival. You don't revive the step. You have some discontinuity and something happening in between. Okay, so we can explain why that is. And it's due to the fact that the spectral structure of the Schrödinger operator with this Robin boundary condition has a unique negative eigenvalue that produces a continuous part in the solution. So you can write the solution as a part that is a pure revival, like the periodic revival, plus another function which is given explicitly here is due to the unique negative eigenvalues, and it's continuous. And so this is an example of linear weak revival. But in fact, this weak revival is all over in the nonlinear problems. That's why this notion, we wanted to make it clear. So again, in that same paper that discussed the linear dispersion, Peter and Gong did a lot of short-time numerical experiments with various nonlinear equations, starting from a step. So NLS, KdV, also non-integrable quartic KdV. They had some results. They looked like some kind of revival is there, but as you know, when you have nonlinearity and a non-smooth initial condition, the classic splitting schemes for evaluating the numerics are not very robust, so they weren't sure if they could trust these results. A few years later, the weak quantization was actually proved by Erdogan and Sirakis for periodic NLS and periodic KdV, in the sense that they proved that the solution is equal the solution of the linear problem plus something else, and the something else is continuous. So it's exactly my definition of weak revival. Yeah, that's what I just said. And then I had a colleague for a couple of years, now she's in Paris, who had just got, in fact, a lot of recognition and big grants for a new type of numerical schemes for studying periodic problems for exactly this kind of nonlinear dispersive equations with rough data. And she has actually rigorous error estimates for these schemes, and they perform really well for long times. So when she was telling me about this, if you're interested in the details, that's a bit the idea of how they work. She said that she got the idea listening to talks on rough paths and this idea of resonances, which is not a million miles away from the kind of manipulation of exponent that either kill or keep the revival property alive. So she said that I asked her, can you do these experiments for me? And she was really happy because she didn't have any natural test for her schemes with a non-continuous initial condition. And so she did a lot of tests, and I'm going to show you what they are. And this is for quite a few things. So this is periodic NLS, a box initial condition. And again, here is the other way around. Red is real and blue is imaginary. But when you get different people doing numerics, they pick the colors as they like. So you can see very clearly that there is some revival. It's not perfect. This is some time, not particularly small, so it seems robust. She had very long times for these experiments. And also KDV, so again, nonlinear. You can see that apart from Gibbs, and this is to be expected, it's there even for the linear problem, but there is also other small deviations from being a perfect revival, but is perfectly evident that it is something like that. She also took an affine initial condition just to see if it's the essential nature of the initial condition gets replicated, and it definitely does. Again, here, as I say, there is this continuous deformation that's due to the additional term in the solution, but the discontinuities are perfectly evident. And then she could also do the full nonlinear PO. And again, you see pretty much the pattern that we proved is the pattern of revival and dispersion in the linear case, also for the fully nonlinear equation. And also a non-integrable example. So this is, again, a discontinuous initial condition for a quartic KdV. So this is not integrable. It has a u cube ux term for the nonlinearity. So strong nonlinearity. So there is no proof here that you can split the solution in the solution of the linear part plus continuous, because those proofs depend on all this Bourgain estimate for the solution of periodic KdV, which are very delicate and hardcore. And they're not available for the quartic KdV. I haven't even tried. Maybe it's possible. But in any case, the numerical evidence is pretty compelling that this is a linear effect that is very robust. Time is not very long. It may be that for a strong nonlinearity, if you keep going, it will kill it. But for a finite time, it's still there. So I remember when I first gave this talk, it was in Leeds, where there are lots of integrable systems people, and they were very upset at this because they thought, no, the integrability must play a role. It clearly doesn't, at least not for short time. I won't make bets that things don't break down if you keep going long enough, but I don't know. Okay, so I'll stop here. I thank you, and these are the people that have collaborated with in various bits of what I've spoken about, and I really have to thank them for a lot of the work. So, and I thank you for listening. Well, I didn't. I wasn't exhaustive. Okay.
So Whittam has this transcendental.
Yeah, and I don't know what would happen.
You expect it to be
So for polynomial or quasi-polynomial thing, what's the asymptotics of Whittam?
Well, it's the same thing that you have for the water. It's the same thing as for the water.
Mm-hmm.
The square of the hyperbolic tangent.
Yeah, I would have to look. For example, as I said to you, you can see it for if you have this dispersion with 5/2, although it's bigger than 2 asymptotically, that doesn't show any sign of supporting revivals.
So another question I have, I think all the equations you had up there were also Hamiltonian.
Mm-hmm. This is.
So these equations are Hamiltonian. So okay, they're PDE, so recurrence is more subtle, but the typical recurrence time for a typical initial condition would be many times lifetime of the universe. But if you within this class of data, can you get like shorter recurrence times, like exact recurrence? Or maybe just pure translation.
Yeah, no, you get exact recurrence exactly at the period. So if you see, when you write...
Oh, but also for nonlinear? Also for nonlinear?
No, linear. I'm talking about linear. For nonlinear, I don't know.
But the nonlinear ones...
Yeah. They're all Hamiltonian. Yes, and I don't know. It's a good question that I haven't thought about, and I should look at. Yes, I mean, and that's proved for NLS and KDV, not for the others.
Is there any way to build that into your solver for the nonlinear problem? Because if you know all the horrible jumps are coming from something that looks like the linear equation, why not just try to build that into a smooth?
Possibly, but I mean, Katerina's stuff handles these discontinuities very robustly, and it does exactly. That's what I was saying. Morally, it does this kind of thing.
So with the third order problem, so if you choose irrational thetas, it's doesn't do revival. So is there a sense in which only very special boundary conditions for that one will be
Absolutely. Yeah, I think the arithmetic properties of the exponents get destroyed very quickly because, well, it's very special boundary conditions. First of all, they give you a self-adjoint problem or a problem with real eigenvalues. The moment the eigenvalues are complex, you can't really expect this kind of modularity to work anymore. So the one I was looking at with Dirichlet condition plus pairing in the first derivative is self-adjoint and conservative, but even for that, I'm not sure.
Questions? If not, let's thank our speaker again.
Thank you.